Okay, in 9.2 now we're going to talk about, well, how confident are we in that proportion number that we found from taking our samples? And that's called a confidence interval for the proportion. So let's start with an example. So in April of 2013, a Gallup poll found that 1495 out of 3559 respondents thought economic conditions were getting better. A sample proportion of p hat is equal then to how many people thought it was getting better versus how many people they talked to. 42%. So p hat 42%, q then would be 58%, the opposite of this, or 100% minus that. So 42% thought it was getting better, 58% did not think so. So we want to try to figure out what the true proportion p is. So we have one measurement, one survey. We think it's the p hat is 42%. So what's the true proportion? The proportion of all people. So again, we can come up with a standard deviation, which is our PQ over N. But notice the standard deviation requires actual numbers. It requires the real P, the real Q, and our sample size. But we're not going to have the real P. We don't know what that is. We're trying to use our sample proportion, our P hat, to estimate P. So what we're going to call it instead of a standard deviation is we're going to call it a standard error. And basically we can think of that as, the error between samples. So we're going to use the p hat that we have, the only number we have. So we're going to say standard error is just p hat, q hat over n. So notice the difference, it's subtle. This is p and q, the actual proportion of success and failure, the numbers we won't be able to get because we're not going to be able to talk to the entire population, versus p hat and q hat. These are the numbers we get from our sample. So we have 42% and 58% divided by how many people we talk to, 3,500, and we get 0.008. And so we can create our normal curve. So we think that it's centered at P, and it's going to go up by that standard error number we just found. So every tick mark is going to be a distance of 0.008 away from P. To the right, we add increments of 0.08. So this is 1.08, this is 2.08, this is 3. And then we subtract on the left side, etc. And so what we want to find out is, we want to look at, well, what's the 2 standard deviation number? So the 2 standard deviation number would be p minus 2 increments of 0.08, so p minus 0.16, and plus p plus 2 times 0.08, or 0.0016. And if we recall from our 68, 95, 99.7 rule, we said 68% of people should fit between 1 standard deviation and minus 1 standard deviation and plus 1 standard deviation. 95% of people should fit between minus 2 standard deviations and plus 2 standard deviations. And even though we're using standard error here, the principle is the same. So 95% of our proportions that we get should fit between minus 2 SEs and plus 2 SEs. And we can figure out what that number is. So if we think that the only number we have for P is P hat, which is 42%. But then we know 2 standard deviations away from that would be 2 times the standard error number of 0.8%. And so we would get 42% plus or minus 1.6. And we would say 40.4% to 43.6%. So again, we don't know the true proportion of people who think the economy is getting better, but what we now can say is that we have a 95% confidence interval that includes the numbers 40.4% and 43.6%. Now let's see how we can advertise those numbers. So what we want to try to say is, okay, well, we took one sample, 3,500 people, which is a nice sample size. That's very large, so we should meet all our conditions. We'll check that at the end. But what we want to say from that sample is, just one sample, what's the true proportion of all U.S. adults who think the economy is getting better. Now, can we say it's 42%? Exactly. Well, no, we cannot, because yes, I took a large sample, 3,500 people, but if I took a sample of a different set of 3,500 people, I can almost guarantee you it will not be 42% as the proportion of people who think the economy is getting better. So we cannot say that exactly 42% of U.S. adults think the economy is getting better. What's a little truer is we could say it's probably true that 42% of U.S. adults think the economy is getting better. But again, we cannot say an exact single number. So what's a better thing to say is, well, we're pretty confident that between 40% and 44%, so rounding a little bit here, if we want to be exact, we're pretty confident that between 40.4% and 43.6% of U.S. adults think the economy is getting better. That is becoming a more accurate statement. Or what might be even more accurate is we could say it is probably true that between 40% and 43.6% contains the true proportion of U.S. American adults who think the economy is getting better. And finally, the best way to say this is we land on we are 95% confident. Why do we say 95%? Because that's 2 standard deviations. So 2 standard deviations away from the mean accounts for 95% of people, or in this case, of proportions. So what we are saying is if we took samples, lots and lots and lots of samples, that we are 95% confident that those samples, the true proportion from those samples is going to be between 40.4% and 43.6%. And statements like this are called confidence intervals. They're hugely important. If you ever see a statistic printed or spoken or otherwise, it should not be a single number. It should always be a range. So a lower bound and an upper bound, and they should report to you the confidence level. So we'll study later how we can go to 90% confident, 95, and even 99% confident. So if it's a serious study and they are reporting statistics to you, they should report 2 numbers, a lower bound, upper bound, and the confidence level. If they're not doing that, you should immediately be suspect of their way they have derived the numbers, and you should look into how did they do their math. This particular method is called a 1 proportion Z interval. So what does it mean that we're 95% confident? Well, there's a couple ways you can interpret this. So we're 95% confident that the true proportion lies between those 2 percentages that we said, which means that on 5% of the time we could be wrong. So 5% of the time you could collect a sample and the proportion is 39 or 47. So the proportion's outside of that range that we advertise. That can happen. And here's an even better way to say it. So in this one, they found 20 more samples and they plotted them. So the green line is the true proportion, the 42 that we found. And these are their confidence intervals. So notice they have a lower bound and upper bound. And then their p hat is the purple dot. Notice that the purple dot will always be exactly halfway between these two, just based on how the math works. And basically what they found is, as long as the green line goes through, touches these orange bars somewhere, then our proportion has captured, then the confidence intervals from all these samples has captured the true proportion. Notice all of them touch the green line except for 1. And if you do the math, 1 out of 20 is exactly 5%. So this is the 5% we got wrong. And that will happen. So we can never say with 100% confidence, well, we can, but basically our interval gets very large, and we'll study this later. It's like the weatherman saying, I'm 100% confident that tomorrow will be between negative 100 and plus 100 degrees. Well, he's going to be right, but that's such a large interval, it doesn't help us. So we have to shrink the interval to a level that is reasonable, that gives us insight, and that means we're going to be wrong every once in a while, and that's okay. That's why we have 95% confidence and not 100. So we can never be sure that our confidence interval contains the true population proportion. But again, with the normal model and with taking enough samples and being random, we can start to say things like we're 95% confident that the true proportion, although we can't get it, is going to be between our two numbers. Again, we have to check our conditions, so independence. We have to make sure we use randomization, 10% condition, so we don't want our sample to be bigger than 10% of the population. That's pretty rare. And then our success failure. We need at least 10 successes and 10 failures, so our sample size needs to be big enough where NP is greater than 10 and NQ is bigger than 10. And that'll do it for 9.2.